Permeability is the last lecture in kind of our background information set of slides. And so what does permeability mean to thermoplastics? The definition of permeability is the amount of gas or other diffusing species that passes through a polymer film. And when you're looking at a polymer film, you're looking at a unit thickness per unit of cross-sectional area. And when you're looking at a gas, it's unit pressure difference per time. The reason permeability is important for thermoplastics, and specifically polymer films, is that these materials are used extensively in food and beverage packaging. The reason that polyethylene terephthalate, PET, is used so extensively in beverage bottles is because of its good barrier properties. And barrier properties are the properties that include how well something is kept out or kept in to a specific material. And polymer films in food and beverage packaging are required to have certain barrier properties. And those barrier properties provide for the fact that they allow only minimal amounts of gases. And these gases can be carbon dioxide, oxygen, nitrogen, water vapor, as well as other things that affect flavors and odors to pass through them. So in other words, if you have something that has a certain level of moisture in a product, you want that moisture kept in. If you want something to stay nice and crispy and not get stale, you want moisture to be kept out. Also, oxygen, if it can freely permeate into your food, can cause off flavors, as well as carbon dioxide. So if you can keep something sealed, in other words, it's exposed to the same amount of gases as it was when it was made, it stays fresher longer. And you have to have those parameters in place if you're using them for food and beverage packaging. I'm going to go through some equations related to permeability. There is also a sample permeability problem in here, in other words, how to calculate how permeable something is. I'm not going to spend time on that particular problem here. I'm just going to define these equations. You will not be asked to know these equations. I'm just putting them out there for you. If later in the semester it becomes apparent that some people are in desperate need of some extra credit opportunities, we're going to come back to permeability. But I will create a separate permeability video, and I will go through that problem in specific detail on how to use these equations and how to solve that problem for your extra credit if that extra credit opportunity needs to arise. So permeability is P, and permeability is the product of diffusivity, D, and solubility, S. Now, the way that permeability is determined is by the Salome method, and it's the simplest and most accurate method for calculating permeability. And it's this concept of Perma Core that's based on structural composition and functional units of a particular polymer. Perma Core is this capital pi here, and its units are calories per cubic centimeter. So this is how you calculate permeability. So P and P star are determined at ambient temperature. P star is a pre-exponential permeability factor, S is a scaling factor, and P star and S are constant for a given diffusing species or a specific gas. So these are things you can find in a table. So the typical gases that you're looking at are things like carbon dioxide, nitrogen, and oxygen. Later on, if you're ever doing any of these, please keep in mind S is very similar for these gases. So this is where people can get goofed up when they're calculating it. Also, you want to keep in mind the units. This is a -11. Make sure it's not a +11 or that can goof you up. But these are assigned constants for a specific gas. This is how you determine a Perma Core value for a functional group. And I won't get into this right now, but if we do this problem, I'll show you how to find your functional groups in this table. So first, you calculate a Perma Core value for an amorphous material, and this is the equation for that. So Perma Core for the amorphous fraction is 1 over n, where n is the number of functional groups in the material, and the summation of those Perma Core values. These can range from 0 for a polyisoprene to 100 for an oriented crystalline polyvinylidene chloride. So these vary widely when you're calculating permeability, and therefore affect your permeability value significantly. If you have a semicrystalline polymer, then you have to calculate first the amorphous fraction and then the semicrystalline fraction. So here is your amorphous fraction from the previous equation. This is Perma Core for semicrystalline, so it's amorphous minus 18 natural log of the crystalline fraction. So this phi right here is the percent crystallinity of a semicrystalline polymer. So if you have a 25% crystallinity, here you have 1 minus 0.25. This is the example polymer, the example problem. I'm just gonna skip past this, but you can take a look at it in the notes, and if you really want to crunch some numbers, all the equations there for you. We may use that one later for an extra credit opportunity, or I may assign a different permeability problem if we need an extra credit opportunity. But the reason why permeability is an important concern is for barrier properties for food, but also the more permeable a material is, the more effect that has on environmental stress cracking. So what's environmental stress cracking? Environmental stress cracking is failure in surface-initiated brittle fracture of a plastic specimen or part under polyaxial stress in contact with a medium in the absence of which fracture does not occur under the same conditions of stress. What? In other words, it's accelerated failure of the plastic due to stress in the environment. And this is highly dependent on a wide variety of things. Molecular weight distribution, comonomer type and content, or the chemical composition, and then crystallinity. And these things also affect the permeability. So generally, environmental stress cracking can be affected by chemicals and solvents, but basically these chemicals and solvents permeate into the material and create chemical attack. So if you have something that's highly permeable, you tend to have accelerated environmental stress cracking. So very bluntly, highly permeable samples will generally show increased environmental stress cracking. So it's not, you want to be able to have some idea of how prone your material is to environmental stress cracking. Also, there's other factors that can enhance environmental stress cracking. Inadequate processing conditions, which creates residual stress within a part. So if you cool something too fast or if you have high wall thickness, they can contribute to environmental stress cracking, or a lack of environmental stress cracking resistance. So permeation is a very brief video, but there is a quiz on permeation that is separate from mechanical and physical properties. So please view this video and then complete your permeation quiz. Thank you.